So we have just seen how we draw electric field lines from one charge or two charges or even distribution of charges. So now let's think about how we can use mathematical expression to express electric fields when there is more than one charge. Okay, so in this figure on the right hand side, we have 9 different charges, and then we want to think about what the electric field will be at this location. And then for each charge, let's call them Qi. So here I will be from 1 to 9, so we can call the charges Q1, Q2, Q3, and etc. And then there's nothing new, but since we have already learned about the superposition principle in Coulomb's law, here is exactly the same thing. The only thing you have to do is calculating the electric field from each charge and then make a summation, in fact a vector summation among them. So using a very simple mathematical expression you probably already know, we can write using this sigma symbol. So we are adding EI vector with I changing from, well, any number, in this case from 1 to 9. Okay, and according to what we have learned previously, the electric field vector includes K, which is a constant. So therefore, it does not really depend on which charge you are talking about. So it doesn't have to go into the summation, so it's standing out. And then the electric field, the size of the electric field will be Qi divided by R square, Ri square. Okay, so Qi will be each charge, and Ri will be the distance between the position you are considering and the charge. Okay, and then one thing you have to take a look at is that this vector, Ri vector, but you see that on top, instead of arrow, you have something called the caret. So what is this? This is actually the same vector as Ri vector, which is the position vector of the position you want to consider with respect to the charge. But then this okay, let me write this Ri caret will be in fact the I vector divided by the size of this Ri vector. So, okay, this is the absolute value. So therefore, this Ri vector is a vector with the unit length. So this is in fact the unit vector. Okay. Okay. And then what if we have a continuous charge distribution? So suppose we have a charge distribution just like this. So it's distributed over this entire volume. So in this case, we cannot really count charges from 1 to certain number. So in this case, we have to take a little bit different approach, and this is a numerical integration. So basically, the basic idea of integration is that you imagine that you are actually having a knife and then cut it off this large volume into small pieces, and this small box inside is one of those small pieces, and then here electric field from this small volume, let's call DEI vector, and then the small volume will be, we can write dV here, just like here, and then this volume will contain small charge, and then let's call it dQ. So therefore, in this case, actually using the same equation, now you can express this small electric field from this small charge using this equation. Okay, looks actually the same. The only difference is that instead of charge Q, you have a small charge dQ. And then you are ready to do the integration. So finally, just like similar to we have done just before, if you have independent or discrete charges, then you are making a summation. But here, integration is actually the same thing. What you are doing is you are still doing the summation, but over the continuous body. So this is how we write. So total electric field will be an integration using this small electric field, And then if you are not familiar with this integration, symbol of this integration with the circle here, what it means is that you are integrating over entire volume. So you are not integrating over a small piece, but you are integrating over the entire volume or sometimes entire area. Okay, that's what it means. So because we have already written what dE vector will be, so what you have to do is simply try to insert it here. Then this is the expression you get. And then you might ask how we actually calculate dq. Maybe you're familiar with making an integration as a function of x or y, but how do we integrate over dq? And in this case, there is a trick. In fact, in order to do that, you have to express the charge density, and then charge density is a charge per volume. So therefore, at each position, now you can, let's call the charge density rho, then it will be dq divided by dv. And then now dq can be rewritten as a rho multiplied by dv. And then if you insert it, now you can express dv as a function of dx, dy, dz. So therefore, now you mathematically you can start to do the integration. Well, of course, in this lecture, we will not do difficult integration. So this is just giving you a basic idea if you encounter such cases, how we do the integration. And I may give you some very simple examples, but do not worry too much. We will not go into very difficult problems here. Okay. And as a similar example, sometimes the charges may be distributed over only a certain area, like 2 dimension. So in this case, we might consider charge density per area, and mathematically it's very similar. Instead of dividing dq by dv, now you are dividing dq by dA, which is a small piece of area. Okay. And then if you sometimes have a wire, and then think about the charge density per length, then what you have to do is dividing dq by dl. And then in this case, similarly, dq will be lambda, which is a charge density per length, multiplied by dl. So again, if you insert this value into the above equation, then you can do some integration following the length of this wire. Okay. Okay, and in this slide, we will study something a little bit different, but very important, and it is electric dipole. So what is electric dipole? In fact, it's very simple. An electric dipole is a pair of 2 equal charges with opposite signs, say plus q and minus q, which are held together by a rigid bond. So take a look at this picture on the left-hand side. This is actually the same picture we have seen previously, and it's rotated by 90 degrees, but it doesn't really matter. See that there is a plus q or positive charge, and then the negative charge, and we already learned how the electric field lines will look like. And here we call this electric dipole, and then the strength of this electric dipole is expressed by the definition of electric dipole moment. Okay, here the electric dipole moment, take a look at how it's defined. We typically call it P vector, and it's defined as a product between Q, which is a charge, and then the D, which is a displacement vector between negative and positive charges. I'm sorry. Okay, so here you can get the idea that if each charge is stronger, then electric dipole moment will become larger. And if the distance between these two charges will become longer, then electric dipole moment will also become larger. Okay, so that's how we define the electric dipole moment. And then why is this electric dipole moment important? It is because there are a lot of chemical molecules that resemble the behavior of electric dipole. And water molecule is the one of the very good examples. So you know that we drink water every day, and a large part of our body is water. So I don't have to explain how important water is to us. And then this figure shows you how the water molecule looks like. As you know, it's H2O, so it has 2 hydrogen atoms and 1 oxygen atom. One oxygen atom is located in the middle, but in fact, hydrogen atoms are not on 2 sides, but they are actually shifted up, as in this figure. And hydrogen atoms, in fact, they are ions. They are positively charged, and as a result, in the oxygen, on the other side, the electrons move to the other side, so it becomes negatively charged. So effectively, it's plus Q along the side of the hydrogen, and it's minus Q along the side of the oxygen. So as a result, it behaves exactly like we have described. It becomes an electric dipole. And then one thing you have to consider is that typically when we say electric dipole, we mean they are very small. If the 2 charges are together, but they are very far away, separated, then well, it is still a dipole, but we are not very much interested in those cases. But just like water molecule, if it's very small and looks like a point, but it still has positive charge on one side and negative charge on the other side, and then this is the electric dipole that we are interested. Okay, and then let's see what will happen if you have an electric dipole located in a uniform electric field. Here on the figure on the right side, we have an electric dipole which is made of plus Q and minus Q, and then the electric field is going from left side to the right side. Okay, and then what will happen? You know, the electric dipole, there are 2 electric charges, so therefore inside an electric field they will experience Coulomb force. So the positive charge will experience the force pushing it to the right, and the negative charge will feel the force pushing it to the left. Okay, but remember, an electric dipole is 2 charges actually held together. So these 2 charges cannot move separately. They have to move together. So as a result, what happens is that they will rotate around the center of mass, which is written as COM. Okay, so when there is a rotational motion like this, we can now think about a torque instead of the force. And then the torque in the spring semester, you probably remember that torque vector, which we use the tau, is defined by the cross product between r vector and f vector. F is of course a force, and r is a position vector of the location where the force is acting with respect to the center of rotation. So in this case, we have 2 forces, so we have to make a summation of these 2 torque terms. So the first term is, let's call the distance between the center of mass and then the location of the first charge as an x. So therefore, in the first term here, we have an x multiplied by the F, which is a Coulomb force, and then the sine theta. So where does this sine theta come from? Remember that in the cross product, when you calculate the size of this cross product, we have to multiply it by that angle sine theta, which is an angle between these 2 vectors. So here we call this angle theta. Okay, and then how about the second torque? In the second torque, we have a d minus x. Now the d is the total length of this dipole, so therefore the d minus x will be the distance between the negative charge and the center of mass. And then F is actually the same because we have plus Q minus Q, the strength will be the same. And then again the sine theta. Okay, and then why did we make a summation? Okay, in fact, in this case, we express both terms to be the positive value. You know that x is positive and d minus x is positive. And then in this case, we have to consider the fact that these two forces are contributing to the rotation along the same direction. So therefore, they are adding up. So the total torque will be the summation between these two. And then if you summarize it, now x disappears. So what you have is that d multiplied by f and sine theta. And then remember that instead of force, we originally had the electric field. So we can replace Coulomb force with QE. And then in the just one slide before, we have learned that the electric dipole moment P was defined as a product between D and Q. So let's replace DQ with P. And then again, remember P and E are vectors. So again, let's see. Okay, this was P vector, and then say this is an E vector. So therefore, angle between them is theta. So again, finally, we can write the torque that an electric dipole moment experiences within an electric field can be written as a cross product between them. Okay, and then this diagram is a summary. And then remember, in this case, following the right-hand rule, the torque vector will be pointing into the screen, and which means that the actual rotation is occurring using the right-hand rule. If you place your thumb along this torque vector, then and then make a fist, then the rotation will be represented by your the other four fingers. So therefore, in this case, the rotation will happen this way. And then if you wait a little while, then electric dipole will be pointing down, because this force actually of torque pushed it down. And then you realize that by making a cross product between these two P vector and E vector, now the torque vector will be pointing not into the screen, but coming out of the screen, just like this. So then in this case, now the rotation will be going, say, opposite direction, which is counterclockwise in this case. So it shows that depending on where the electric dipole moment is pointing, the torque will be acting opposite direction. So as a result, this electric dipole moment will be oscillating about the direction of the electric field. This is a very similar case as we have studied in the spring semester about the pendulum motion. So basically, it's an oscillation. Okay. And given this situation, think about again the pendulum case. The reason why the pendulum was oscillating was because there was a potential energy or the gravitational force which was pushing the pendulum downward, but it could not stop because there was a kinetic energy. So therefore, but even in that situation, we could calculate the potential energy of the pendulum using the gravitational force. Now, similarly, in this case, the potential energy of a dipole can be calculated. Now, in this time, because the rotational energy, instead of force, we can use the torque to calculate the potential energy. So basically, in this case, the potential energy of the dipole in the uniform field can be calculated as the work done by the field to rotate the dipole from 0 angle to a certain angle. Oh, I'm sorry, this is a typo. Okay, instead of Q, it has to be certain angle theta. Okay, I will make a correction. Okay, and so to write it explicitly, now the potential energy is equal to the work, and then we have to do the integration of the torque as a function of angle theta. This is similar to doing the integration of torque, integration of the force with respect to the displacement. Now, but in this case, it is the angular displacement, okay? And then torque was PE multiplied by sine theta. And then remember, in this case, P and E are constants, so what you are integrating is just a sine theta. And then you know very well it will become minus cosine theta. And then if you insert that the angle theta changes from 0 to a certain angle theta, then this is what you get. And again, try to remember that the potential energy, the absolute value of potential energy is not important. Only their differences are important. So therefore, the first term, which is PE, actually doesn't really matter. So we can just simply drop it. And then now we have minus cosine theta and PE. And then again, remember PE are vectors. And then, so therefore, we can express it using the scalar product or dot product between these two vectors. And then again, okay. And then finally we can say that the potential energy of the dipole in a uniform electric field can be expressed using a dot product. Okay, so try to remember it's very simple. The torque will be the cross vector, torque will be the cross product, and then the potential energy will be the dot product. But remember, there is a minus sign. Why minus sign? Because when these two vectors are parallel, we want to make the value the smallest. So when they are parallel, actually P dot E becomes the largest. So the simple way to make it the smallest will be just putting the minus sign here.